Okay, here's an example of how to do a curve sketching example from start to finish. So if it was a quiz or the midterm or the final, I would give you the function and also f prime and f2 prime. That way you don't spend time just doing out the derivatives, and mainly because if you were to make a small mistake in finding one of those two, your whole graph gets messed up. So for a assessment of any kind, I would give you all three functions, and then just you would have to know what to do with it. One other note though, for the p-sets, I don't do this. And when you're doing your p-set, make sure that you simplify f prime and f2 prime before doing your analysis. So use algebra, use your trig IDs to simplify the expression, then do all your analysis. That is my hint for the p-set. Okay, graph sketching. First, the function. The function gives us two things, intercepts and asymptotes. So the x-intercept, that is where the top is 0, so we get -3 and +3. Those are the coordinates of the intercepts. The y-intercept is what you get when you plug 0 into your equation. When you plug in 0, it gives you 9/2. So those are 3 points on our graph that we know from where the graph is 0 and where the graph is at x equals 0. Asymptotes. Vertical asymptotes occur when you divide a non-zero number by 0. Since this function is rational, we might have vertical asymptotes. For polynomials, you wouldn't have any. But here, if we plug in 2 or -2, we get a non-zero value over 2. So those are vertical asymptotes. The horizontal asymptote, that is the limit as x approaches infinity and -infinity of our function. Now, as x goes to infinity, these constant values essentially become nothing, and our function turns into 2x squared over x squared. The x squareds cancel out, and so our function essentially turns into 2. For huge values of x, our function turns into 2. If it was x going to negative infinity, same thing happens, we get 2. So we have one horizontal asymptote, it's 2. So now we know where our graph is, and we know lines that our graph must follow. A whole bunch of 2's. Next, f prime. From f prime, all that we do right now is just get the critical numbers. The top is 0 at x equals 0. So x equals 0 is the critical number. That is where the slope is 0. F prime does not exist when the bottom is 0. That's at 2 and -2. Then I cross those off. I cross those off because in order for a point to be a critical number, the function has to exist there. And our function does not exist at those 2 points. Those are asymptotes. If you forgot that and you left them as critical numbers, nothing actually changes for your math. It's just they aren't critical numbers, so I'm going to cross them off. And then f2 prime. Where does our graph change concavity? We set the top of f2 prime equal to 0. It's never 0, because 3x squared plus 4 is never 0 for the real numbers. And the bottom is 2 and -2. So we cross those off, because those are not points where a function exists. So we have no possible inflection points. So no points on the graph will have a change in concavity. Concavity might change, it's just if it does change, it happens at the asymptotes. So that's your first step. Find the intercepts, find the asymptotes, find the critical numbers, find the possible inflection points. Next, we make our table. For the table, we consider all the x values where the shape of the graph might change. Now, the x-intercepts will not correspond to a change in shape. That's just where the graph is. But asymptotes, vertical asymptotes, are x values where the shape might change. And also critical numbers are points where the shape might change, and inflection points, which we don't have. So when you make your table, you include any vertical asymptotes, any critical numbers, and any inflection points, which we don't have, so that's blank. And then you split the real line using those points of interest. And now our table is going to be a little bit bigger, because we have two things that we care about: the increasing, decreasing behavior, and the concavity. And then you plug them all into the derivatives. So I wish I had saved my derivative here. So we plug in -3. When you plug in -3 to f prime, actually I'm going to write down f prime again. F prime was 20x over x squared minus 4 squared. Cool. So one thing to note is x squared minus 4 is being squared, which means that that is always positive. Doesn't matter what number of x you plug into it, it gives you a positive number. So really all we care about is that 20x. When we plug in our test values, is that positive or negative? For -3, it's negative. So we'd have a negative number over a positive, negative. For -1, also negative. For 1, it's positive. For 3, it's positive. So we pick a number from each interval and we plug it into f prime to see what its sign is. For f2 prime was -20 3x squared plus 4 over x squared minus 4 cubed. 3x squared plus 4 is always positive, because when you square a number, it either goes positive or to 0. When you add 4, it goes positive for sure. So all we really care about is really this. Is this value negative or positive? For -3, that's positive. So you'd have negative over positive giving you negative. For -1, it would be negative over negative. For 1, it's positive over a negative. Oh, sorry, it would be a negative over a negative, so positive. And then for 3, it would be a negative over a positive, negative. So again, plug all those test values in, see what sign you get. Now, this is actually a nice little guide here. And also, if you go to the lecture notes on Stellar and look at it, I have a little handy guide. This is every possible combination of plus and minus for f prime and f2 prime. And this will give us the 4 main shapes of a graph. If a graph is negative f prime, negative f2 prime, it means it's decreasing and concave down. That looks like this. So that gives you that shape. Decreasing concave up looks like this. Increasing concave up looks like this. Increasing concave down looks like this. So those are the 4 main shapes, and every graph that you'll study is some combination of those shapes. And this kind of matches each shape up to how it looks on the graph. And so now we make our graph. So, there we go. Make a quick sketch. First we put intercepts, 3 and -3 and 0, 9 halves. Oops, sorry, I'm off the screen. Well, that's not helpful. There we go. Then we put the asymptotes, y equals 2 is the horizontal asymptote, x equals -2, x equals +2. And now we use the table to figure out where the graph actually is. So, from -infinity up until -2, our graph has to have that shape. I'm trying to fit everything on the page at the same time. That's good enough. So the only way to have that shape and to fit this graph is if it's right here. Right? Because that shape can't go up here. It wouldn't fit the shape of the asymptotes or the graph. So when you sketch your graph, you have to use the shape and match it to the asymptotes and the intercepts. Next. we have decreasing and concave up. So it's that shape, which is going to start up here and then go to there. And then after that, we have that shape, which completes the U shape in the middle. And then we can probably guess that we're down there, and sure enough, that's the shape our graph has to be. So when you do this last step, when you make your graph, you put the intercepts and the asymptotes, and then you use your table and the shapes that the table gives you, and you match them all up in your graph. Okay. And don't forget, come to office hours if you have any questions on any of this.